From orbit, a mature tropical cyclone presents as a structured thermodynamic machine. Its clear eye, dense eye wall, and spiral rain bands function as a planetary machine. At the surface, the machine's interaction with land erases the coastal grid, pushing deep floodwaters across peninsulas and overrunning local infrastructure. This system generates power at a rate equivalent to the detonation of a nuclear weapon every few minutes. Mapping the machine's anatomy reveals the specific, fragile physics that allow it to self-assemble over the open ocean. This cross-section diagram illustrates the 3 strict prerequisites required to birth a cyclone. You need ocean water heated to at least 26.5 degrees Celsius, high atmospheric instability so air can rise easily, and low vertical wind shear, meaning the winds at different altitudes are moving at similar speeds and directions. The engine sparks to life when warm, moist air rapidly rises from the ocean. As this air pulls upward, it leaves behind a localized low-pressure vacuum right at the sea surface. Because the Earth is rotating, a phenomenon known as the Coriolis effect bends these rising air currents. This imparts angular momentum to the system, forcing the once disorganized cluster of clouds to start spinning around that central vacuum. Once that rotation locks in and the ocean heat crosses a critical threshold, the storm hits a tipping point. It achieves a self-sustaining state, operating independently of the initial weather disturbance that triggered it. Deep inside a mature storm, the physics become paradoxical. Right at the center, the pressure dynamics actually force air to sink rather than rise. This downward motion suppresses cloud formation, creating the dead, cloud-free calm of the eye. Immediately surrounding that calm is the eye wall. This tight ring contains the storm's most violent updrafts and heaviest precipitation. The clouds here naturally extend outward with altitude, creating a towering, sloped cylinder that meteorologists call the stadium effect. The storm fuels its own violent growth through a continuous feedback loop. It evaporates massive amounts of warm ocean water, which eventually cools and condenses at high altitudes. That condensation releases latent heat, which in turn powers even faster rotation. When this feedback loop operates without interruption, it triggers rapid intensification. This is a highly dangerous phase where a storm's maximum sustained winds jump by 35 miles per hour or more in a single 24-hour window. By converting vast quantities of oceanic heat into concentrated kinetic energy, the mature cyclone functions as a self-fueling engine, its power ceiling determined entirely by the temperature and depth of the water beneath it. This tracking map shows the historical paths of tropical cyclones across the Atlantic and Pacific Oceans. The sweeping westward lines you see are dictated by environmental steering, the process where large-scale, background planetary winds push the cyclone across the ocean like a leaf carried by a stream. Notice where those historical tracks curve sharply to the north, breaking away from the equator. That secondary push is called beta drift. The storm's own cyclonic spin continuously interacts with the Earth's varying Coriolis force, which nudges the entire massive system slowly poleward and westward. Depending on exactly where this drift takes them, human geography dictates their title. In the North Atlantic and Northeast Pacific, they are hurricanes. In the Northwest Pacific, they are typhoons. In the Indian Ocean and South Pacific, they are simply tropical cyclones. Regardless of the local naming convention, the internal mechanics are identical. They are bound by a unified set of planetary physics that mathematically dictate whose coastline is in the crosshairs. The moment a cyclone makes landfall, its death sequence begins. Cut off from the warm ocean water that acts as its fuel, and choked by the heavy physical friction of terrestrial landscapes, the internal circulation rapidly breaks down. But a decaying storm still must offload its stored energy. It does this by driving a physical wall of ocean water ashore, the storm surge, and dumping overwhelming, continuous rain that leaves standing water reaching the rooflines of residential homes. Simultaneously, the extreme kinetic wind energy stored in the eye wall whips through the interior, snapping heavy utility poles and physically dismantling the coastal power grid. It is a dark physical irony. The exact moment the storm begins to permanently die, is the exact moment it inflicts the maximum physical trauma on human civilization. Today, the rules of cyclogenesis are shifting. As the addition of heat to the global oceans expands the potential fuel supply, the environmental thresholds for these storms are met more often and with higher intensity. The Clausius-Clapeyron relation shows that warming atmospheres hold exponentially more water vapor, translating into extreme multi-day rainfall reaching further inland. This trapped heat also redraws the global map, expanding the storm's thermodynamic loops poleward into regions that previously never saw them. Tropical cyclones act as the Earth's mechanism for balancing trapped heat. As we continue to warm the globe, these thermodynamic engines will run hotter, larger, and longer, forcing humanity to rethink exactly how and where we choose to survive.